Although the goal is to ultimately unify the four forces, they are finding that even threefold unification is a distant landmark. The theories which unite the strong, electromagnetic, and weak forces are called grand unified theories. There's no machine powerful enough to test them in the same way that the electroweak force was tested at CERN. But the grand unified theories do make three concrete predictions about the existence of matter that don't require high energies for confirmation. If any one were found to be true, it would be strong evidence that physics is on the right track. The first and perhaps most startling is the prediction that the basic building block of matter, the proton, should decay. Such decay is predicted by the symmetry principle. It works like this. Different particles are affected by different forces. For example, quarks are affected by the strong force, which binds them into protons, while electrons feel only the electroweak force. So if these two forces are linked by symmetry, then the particles are as well. So quarks and electrons must be interchangeable. A proton is a combination of three quarks. If one were to be replaced by an electron, the other two remaining would no longer make up a proton, and the particle would literally fly apart. Since nearly everything in the universe is made up of protons, the unification theory implies that given enough time, our entire world will disintegrate. It sounds alarming, but the process is so rare that in this tank of water only 1 or 2 protons are expected to decay a month. The experimenters hope that by waiting and watching long enough, they'll be able to spot a proton breaking up and sending off photons, or tiny flashes of light, to the 2048 sensitive phototubes lining the walls. It's a long wait. In fact, a team from the University of Michigan, the University of California at Irvine, and the Brookhaven Laboratory has been standing by to observe a decay since the summer of 1982.
Okay, so we can then shut off this run.
The snag is that cosmic rays may mimic the process. So the IMB team buries its experiment some 2,000 feet underground in the caves of a salt mine near Lake Erie. Several similar experiments have found homes in equally exotic surroundings. But even at these depths, some unwanted particles still get through. At the University of Michigan, computers are busy trying to spot the rare patterns of light that would signal proton decay. A reconstruction of exactly when each phototube was hit reveals some quite distinctive features. But are they what's expected? Proton decay should be recognizable by characteristic back-to-back signals, the light from which will illuminate just a few phototubes in any cross-section of the tank. There are 2 types of cosmic ray particles which produce signals that can confuse the experimenters. One of these is the muon, produced high in the atmosphere. Thousands of these penetrate the tank each day. Its signal appears as complete walls of phototubes lit up in a continuous swath of light. The second offending particle, the neutrino, interacts with the water and produces a light pattern very similar to proton decay. Since 1982, millions of events have been recorded. Most are unwanted background. But what of the remainder?
The experiment's gone extremely well. We have not found the expected events which were on the simplest version of grand unified theories. This is a little bit disappointing and somewhat embarrassing to the theoreticians, but I would say at this moment it doesn't rule them out, but it's a little bit embarrassing for them.
So far, the evidence for proton decay remains inconclusive. The second prediction of the grand unified theories is the existence of an unusual particle called a magnetic monopole. Sheldon Glashow explains.
When Maxwell made his theory that put together electricity and magnetism, he noticed something. He noticed that there could exist particles that have an electric charge that are the sources of electric fields. A few years after his theory, these particles were discovered. They are called electrons. There could also exist particles that are the sources of magnetic fields, from which magnetic fields come. He imagined that those particles also exist. But it seems they don't, or at least until the present. Nobody has ever found a particle from which magnetic field comes. If I may make that picture on this piece of cork, an electron, for example, E for electron, is a source of electric field. That means coming from it, there's an electric field that points out in all different directions. Now, a magnetic monopole is exactly the same thing. It's a fundamental particle which is the source of magnetic field lines. A magnetic monopole, a hypothetical particle, from which magnetic lines of force would come out in all directions. Now, the only kinds of magnetic systems we can make are things that look like this, magnets. Magnets are things that have a north pole and a south pole. They do produce a magnetic field, but the magnetic field comes from one side and goes to the other. It has lines of force that look like this. Now, what a magnetic monopole is a north pole without an associated south pole. So you might say, that's simple, just break the magnet in half and you have a north pole and a south pole. But it doesn't work like that, because a north pole is created here and the south pole is created here, and you end up with a smaller magnet. You can imagine doing this again and again, continually cutting a magnet into smaller pieces. You finally end up with a single atom, which is also a magnet, but it too has a north pole on one side and a south pole on the other. You can tear the atom apart. You end up with an electron. The electron is also a magnet, but it has both a north pole and a south pole.
According to threefold unification, these monopoles would be very heavy particles, so heavy that current accelerators are unable to create them. You'd need an accelerator 100 trillion times hotter than what we have today.
There was an accelerator of just that kind once, and only once, in the history of the universe. The original Big Bang, the tremendous explosion from which our universe evolved and is still exploding, this explosion was of an immense energy, far beyond any energy we can produce or will produce in the laboratory. It was energetic enough to make magnetic monopoles, if there are such things.
If such exotic particles do exist, where does one start to look for them? Do physicists have any guidelines?
Now, the logic that is employed in this search is that which the French call the logic of the lamppost, which goes as follows. Suppose you go back to your home at night, a little drunk and walking, and when you get to your doorstep, you find that you have lost your keys. Where are you going to go back and look for your keys? Well, you will look for your keys under the lamppost, because should they be in the dark, you wouldn't find them anyway.
The best place to find monopoles seems to be underground, where researchers also look for proton decay. Monopoles flying through matter are expected to trigger or catalyze the decay of a number of nucleons.
Imagine a monopole moving through the detector, catalyzes one nucleon decay, catalyzes another nucleon decay, and so on. So we would see a sequence of nucleon decays separated by a short time interval. And that's a very characteristic signal. We look for that. We haven't found any evidence for it.
But the fact that no monopoles have been found is not conclusive evidence that the grand unified theories are wrong. After all, no one knows how many monopoles there are or where in the universe they might be. The third prediction from the grand unified theories concerns the ever-elusive neutrino. This particle, produced by nuclear reactions in the sun, was originally thought to have no mass at all, like a photon of light. But recent work suggests that it may have a mass after all. Some scientists are now going to great lengths to measure it. One of the best places to look for neutrinos is under the core of a pressurized water reactor. Such nuclear power generators provide an abundant and controlled source of neutrinos. If a neutrino is found to have any mass at all, it would support not only threefold unification, but also theories about the fate of the entire universe as well.